Good. So hello everyone. So let's start the afternoon session. The first speaker will be Sunil Chhita, and he will tell us about Gaussian orthogonal fluctuation for the maximum of the top path in alternating sign matrices.
Okay, so thank you, and I'd like to thank the organizers, in particular Filippo, for organizing this fabulous conference, especially in the middle of a pandemic. Okay, so this is some joint work with Kurt Johansson and Arvind Dyer. So Arvind is now in Florence. He just arrived. Okay. Okay. So the overview of the talk is first I'll give some brief history on alternating sign matrices, which is also the six-vertex model. I probably won't cite everybody that should be cited. I'm new to the six-vertex model, so I understand, people work from this model in physics, and I'm coming pretty much from a combinatorial / probability background, so I apologize if I miss your name out. Then, in order to get some intuition, we'll look at random domino tilings of the Aztec diamond, which we saw yesterday and also today in Maurice's talk. I'll tell you what the F1 and F2 Tracy-Widom distributions are very briefly. Then we'll look at large ASMs, which is the thing that we're particularly interested in, and formulation of the main theorem. And then I'm going to give a sketch of the proof of the theorem. So I presume, there's lots of people in physics here and lots of people in probability here. So I thought maybe we'll do an introduction in combinatorics. Okay, so we're going to let M be an n by n matrix. And I'm going to let I and j be a subset of 1 to n. And the number of elements in I and the number of elements in j are the same. And I'm going to let M subscript ij be the matrix where I remove the rows in I and remove the columns in j. So Dodgson in the 19th century found an algorithm for computing the determinant. And it's as follows. So the determinant of M is equal to the determinant where you remove the first row and first column, multiplied by the determinant of M where you remove the last row and last column, minus by the determinant of M where you remove the first row and last column, multiplied by the determinant where you remove the last row and first column, and divided by the determinant where you remove the first and last row and first and last columns. Okay, so he computed this determinant. So if you like this in pictures, what this looks like is you've got the determinant, I'm just going to scribble out the first row and first column. So it looks like this. So this is, I've removed the first row and first column, last row and last column, first row and last one, and then first row and last one. And then I divide it by the determinant where I remove the first row and last columns, okay? So a generalization of this is to replace this minus sign by a lambda. Okay, and this is called a lambda determinant. Okay, and one of the questions in the 80s is, for this relation, is there a specific formula? Okay, and it turns out that there is. And in order to give you this formula, I need to tell you what an alternating sign matrix is. So an alternating sign matrix of size n is just an n by n matrix with entries in 0, 1, and -1, such that the sum of each entries in each row and column is equal to 1, and the number of non-zero entries in each row and column, the non-zero entries in each row and column alternate in sign. So you'll get a 1, some zeros, then a -1, some zeros, and then a 1, etc. So for example, there are 7 alternating sign matrices of signs 3, and they're given by these 7 matrices here. Okay? So you can see that the first non-zero entry in each row and column, and also the last non-zero row in each row and column is a +1. Okay? Right, so what Robbins and Rumsey found was this generalization of the determinant, this lambda determinant, has a nice formula. Okay, so in terms of like these ASMs, so n negative a is just the number of minus ones in an alternating sign matrix, and the inversion of a is just defined through this formula. Okay, so they found this nice formula where you're summing over the alternating sign matrices. So this led to the question, how many alternating sign matrices are there? Okay. So in fact, it took quite a while to answer this question, but let me tell you a model which is actually equivalent to alternating sign matrices. And this is actually the six-vertex model. So if you have the six-vertex model with domain wall boundary conditions, so what that means is that you restrict your six-vertex model to a square, and you have outgoing arrows on the bottom and top, and incoming arrows on the side. So here is a configuration with the domain wall boundary conditions. So I've got a size 3x3 square, and I've got outgoing arrows on the bottom. Okay. And incoming on the left and right. Okay. Right. So that's what this domain wall boundary conditions are. And all the six-vertex model is that for each site or for each vertex, you have two incoming, you have two outgoing arrows, and there are 6 possible configurations that you can get. Okay. And the way that you get between the six-vertex model and ASMs is by this relation here. So if I gave you a six-vertex configuration on this square here, you could write down the alternating sign matrices just by using this dictionary here. Okay, but if I gave you an alternating sign matrix, so if 1, 1, 1, 0, 0, 0, 0, 0, 0, you can also recover the 6 vertex configurations. And the way that you do that is just follow the dictionary. So you know that you've got these boundary vertices, these are given. And then you just fill in where the ones are. So the ones are this one, and it's incoming, or let me draw like this. Okay, so I've got incoming here and outgoing there. I've got a 1 at this point here, which corresponds to that one there. So I know what this one looks like. Okay, and then I've got a 1 on this bottom right, so that I know that I've got this. And then you just fill in the rest, because now you've got a place where you've got 3 arrows known, and because you know that you need to have 2 incoming and 2 outgoing, you can just fill in that one. So this one is that. Okay, and now this induces this one to have 3. Okay, and so you know that you've got 2 outgoing and 1 incoming, so this needs to be an incoming, and then you just proceed. Okay, so that's the dictionary. Okay, so 6 vertex model with domain wall boundary conditions, yeah? Oh, for periodic boundaries, I guess the ASM doesn't really make sense for periodic boundaries, but yeah, I guess something similar could be done. I'm not sure. Good question. Ah, yeah. Yeah. Okay, right. So let's have a small digression on the 6 vertex model. So the 6 vertex model is quite an old model. It was introduced in the 30s and has a very rich history in StatMac. And normally what one does is one introduces weights, A's, B's, and C's, okay? And then the probability that you pick a configuration is just the product of these vertex weights, or proportional to the product of these vertex weights, so the usual Boltzmann measure. And there is a parameter delta, which is a squared plus b squared minus c squared divided by 2ab. Okay. And this model is parameterized by this delta as opposed to the individual weights. Okay. So if you fix, it's just enough to tune delta to some number. Okay. So what we're interested in is uniformly random six-vertex models. So this is when you set A, B, and C is equal to 1. And if you do a computation, this just corresponds to delta is equal to a half. For those in theoretical physics, they probably know that Lieb in the 60s computed the free energy. Okay. Right, so let's flip back to combinatorics from where we started off. So Mills, Rumsey, and Robbins conjectured that the number of ASMs, so the number of six-vertex configurations with these domain wall boundary conditions, has this really nice product form. So it's 1, 2, 7, 49, 49, okay, etc. And it took a while for this conjecture to be settled, but it was first settled by Zeilberger, who gave quite a long proof, and then settled by Kuperberg, who gave a much shorter proof. Okay. So Zeilberger's proof, what he did was he showed that ASMs are equinumerous, so the number of ASMs has the same number as another model called totally symmetric self-complementary plane partitions. Okay? And the formula for these totally symmetric self-complementary plane partitions had already been computed. So I'm going to tell you what the TSSCPPs are a little bit later in the talk. Kuperberg's proof was a bit different. So he exploited this link between ASMs and the six-vertex model with domain wall boundary conditions. And the partition function for this had already been computed. So Koropin, he was able to Isogen was able to find a formula for this based on some recurrence relations that Koropin gave. It's known as the Isogen-Koropin determinant. Okay, so I should make a disclaimer. So for anybody that's worked on these models, it seems like a rite of passage to spend 3 months of your life trying to find a bijection between these models. And so far, nobody has found one. Depends on who you talk to. I don't. Well, so we got into this because we were looking at, like, I kind of thought that maybe if correlations, I wanted to look at correlations for TSCPPs, and I haven't been able to see anything that relates apart from the thing that we've done. So I don't really think that there exists, but maybe I'm not an expert in this, but there's a claim. I guess the thing is, there's probably, you can find a bijection, but you can't find a useful one that preserves statistics, or like, I don't think there's one that's local, for instance. But others might have different opinions, I guess. But there is another model called descending plane partitions, and Fisher and Kovalinka gave a really, really complicated bijective proof between ASMs and descending plane partitions. It's not really clear that it's actually functional or useful, but it is some kind of mapping from one configurations to the other configurations. So this I should mention that this last thing involves 2,000 lines of code. So I think it's pretty complicated. Right, so let's move to a model that we saw earlier to actually give some intuition behind what's happening in these types of models. So a useful model is one that we saw earlier, which is random tilings. So they explain to us, like, what are the limiting things that occur. So as we saw earlier, an Aztec diamond is this thing here. So I'm drawing the dominoes here, not the diamond configurations. And here is just a domino tiling of the Aztec diamond. So yellow is horizontal and green are horizontal, and then red and blue are vertical. And a tiling is just that an arrangement of dominoes so that each square is covered exactly once by a domino, and there's no overlapping squares. Right, so as we saw earlier, when you look at uniformly large random tilings of dominoes, what you get is this limit shape phenomena, okay? And so you get this emerging circle that appears, and you get these two regions here for this particular model when it's uniform. You get these frozen regions where you get brickwork structures of tiles. So these are drawn in the blue, red, green, and yellow. And then you get this rough region where you get a disordered mess. Okay, so that's like the law of large numbers result. So what people are interested in, or what's kind of interesting, is can you say anything about fluctuations? And there are a few results that you could look at. You could look at like what happens in the bulk, or what happens in the edge, or what happens at these tangency points. So let me just mention two results. What happens at the frozen rough boundary is that you get the Airy 2 process. I'll tell you what that is, or remind you what that is in a second. And at these tangency points, you get something called the GOE corner process. So let me just remind you what the Airy 2 process is. And I should just mention that there are general results on limit shapes that we saw yesterday, and also due to Cohn, Kenyon, Prop, Kenyon and Kunkov, and this recently, Arstella, Duza, Proza, and Zhong found some really interesting results on the limit shape and a bit further than the limit shape. Okay, so one way to define an Airy process and the F1 and the F2 distributions is to look at Dyson Brownian motions. Okay, so what we're going to do is we're going to start n independent Brownian motions started from the origin and ending after time n. And these guys are conditioned not to intersect. Okay, so you get a picture like this. So this right boundary is free. Okay, so they're allowed to end wherever they want. Okay, if we zoom in to this point that's away from the origin and away from this right boundary, okay, and we zoom in such a way that we don't lose any paths, and that the distance, the average distance between the paths is order 1, then we get the Airy process. So this top line converges to the Airy process. If we look at one time point of this Airy process, we get the GOE Tracy-Widom distribution. Okay. And another thing is that if we look at this right boundary and we look at where this top path hits this right boundary, if we center and rescale in the right way, we get the GOE distribution, so Tracy-Widom GOE distribution. Okay. But there's also another way that you can get the Tracy-Widom distribution, GOE distribution. If you take the Airy process minus by a parabola and then take the maximum, then you get the Airy process. Okay, sorry, the GOE distribution. So let me just mention that. So GOE in two places. One is free boundary, because we'll want this for later. And max of Airy minus a parabola. Okay. Right, so as this workshop is called randomness, integrability, and universality, let me just mention that these random matrix theory limit laws are, should be universal, and they've been proved in quite a few settings. So first is when delta is equal to 0. So this is exactly domino tilings. Also, some directed last passage percolation models, polynuclear ghost models, TASEP, there's a whole list. Okay. But these rely on like you having some specific structure behind the models that they're determinantal. And there has been some progress in the recent decade when there is no, where the underlying structure is algebraic, but the models aren't necessarily determinantal. Okay. So one result, for example, is Borodin, Corwin, and Gorwin considered edge fluctuations for the stochastic six-vertex model. So it's a six-vertex model with a different parameter as delta. And they found that fluctuations are given by GOE distributions. Okay. And in recent times, there's been some big understanding on the algebraic structure, but I won't mention that here. Right, so let's get back to ASMs. Okay, so what we're going to do is we're going to rescale our ASM by n, so it fits in a 0/2 square. Okay, so if we use our intuition from what we found for random tilings, what we expect to see is 4 frozen regions and a disordered region inside. And Filippo with Pronco and also with Sportiello using 2 different methods actually predicted these limit shape curves. Okay, and it was made rigorous by Amol, okay, and they found that it's part of an ellipse. So you get 4 parts of an ellipse stuck together. Okay, so the limit shape is known. So at the corners, Vadim Gorin showed that at the tangency points, you get the GOE corner process. So it's like the random domino tilings of the Aztec diamond. So can we say anything about the edge fluctuations? Okay. So in order to say something about the edge fluctuations, we first need to give a good description of the paths, or what's happening at this boundary. So we need to do a transformation. So the first thing that we're going to do is we're going to change our matrix A to this matrix C. So A is n plus 1 by n plus 1, and C is n by n. And the formula for C is just given by this thing here. So you can go from my A's to C's and C's to back. It's bijective. Okay. So for example, if you start with this identity matrix, you do this computation, then you just get 1, 1, 0, 1. Okay? So you can do this with all the 7 matrices, all the 7 alternating sign matrices of size 3. Okay? So you can just do this. Now, these things, if you plot them in the right way, they look like heights. And they look like the level lines, and the gaps between them are like the level lines of a height function. So what we've done here is I'm just taking this matrix here, I'm just arranging it in this structure here, and then these lines in red just represent the boundaries. Okay? So if I go from this face here to this face here, so you notice I've gone up in height, so I just mark where I've gone up. Okay? So this gives me a good non-intersecting path description of my alternating sign matrices. Okay, so we've now mapped our 6-vertex model configuration, or ASM configuration, to a non-intersecting path ensemble. Okay, so here is a size 9 alternating sign matrix. Okay, and I'm going to rotate it. Oops, I'm going to rotate it by 45 degrees. So I've just flipped the picture. Okay. And now I'm just going to introduce coordinates. Okay. So I'm just going to say that this vertex here has coordinate negative n0, and I'm just going to assign Cartesian coordinates. Okay. Now, what I'm going to do is I'm going to look at the coordinates of the top path as I go from left to right. Okay. So if I look at this point here, it's height 0. Then I go along, and then it's height 1. Go along, it's height 2, height 3, height 4, etc. Okay. So I've got a vector of heights. A vector just containing the heights as I go along the top path. So our main theorem concerns the maximum that this top path reaches and the fluctuations of it. Okay, simulation break. So this is an alternating sign matrix of size 100. Okay, and the limit shape is overlaid. And you can see the top path here. Okay, right. So I'm going to introduce constants alpha is equal to 2 minus square root of 3, and C0, which is equal to 1 over 2 times 3 to the 1 over 6, okay? So this is the scale factor. I'm going to let F1 and F2 be the GOE and GUE distributions, respectively. So our main theorem is that if you look at the maximum of the top path, you minus by 1 minus alpha times n. So essentially you're minusing by this distance here, so you're getting rid of that. Then you divide by C0 n to the 1/3, so that's like the size of the fluctuations. Okay. If you look at this object, this converges to Tracy-Widom GOE distribution. Okay. And what we get is, from this we get a believable conjecture that this gives us evidence that the top path should hopefully converge to the Airy 2 process. In particular, if we just looked at the path at time 0 here, if we minus by the same things and multiply the scale factor by 4 to the 1 over 3, we should get the Tracy-Widom GUE distribution. Okay. Yeah. No, it's kind of encoded in the thing, right? It's kind of encoded there. It's like it's encoded because we're like, you know, we're up here, right? We're already at the origin. Okay, so let me say a few words about the proof. So before I tell you about the proof, I just have to tell you that everything, although I told you that the GUE and the GOE distribution in terms of these Brownian motions, there are really formulas involved in this. So I should tell you what the formulas are. So you've got AI is just the Airy function. And we're going to introduce this 2x2 block kernel. Okay, so KGOE is just 2x2 blocks. And then I've got formulas for KGOE11, K12, K22. So these are just something in terms of Airy functions. Okay, so you can just take them as something involving products of Airy functions. Define a Pfaffian. So Pfaffian is just, you take an anti-symmetric matrix, take its determinant, then its square root. That's the Pfaffian. And then the GOE Tracy-Widom distribution is really defined as a Fredholm-Pfaffian. So the Fredholm-Pfaffian is just an expansion. It's just this expansion here. Okay. And J here is this matrix 0, -1, 1 on the diagonals. Okay. So that's the object that we want to get. So it's really on the level of formulas. Yeah. Oh, I didn't. I think I wrote it there. Yeah. Okay, so how did we prove this thing? Maybe others might disagree with this statement, but I feel like there's no amenable formulas for ASMs. So Filippo has a series of works with Pronko on the emptiness formulation probability, but we found them pretty difficult to analyze to actually say anything concrete. Ilse Fischer also has some similar formulas that they have the same level of difficulty. So it's amazing that you can actually write a specific formula, but it's a bit annoying that you can't actually, it's a bit hard to actually analyze them. So, you know, we couldn't make any progress that way, but that could be one way to go. So actually what we did was we used Zeilberger's results to relate statistics of ASMs to TSS-CPPs. Okay. And we then used formulas that I had with Arvind to analyze relevant events in TSS-CPPs. And then we performed an asymptotic analysis to obtain the results. So that's like the main step. So I'm going to go through a little bit more about them. Okay, so let me tell you what a TSS-CPP is. So totally self-symmetric plane partition. So a totally cell-symmetric plane partition is a box plane partition with the maximal type of symmetries, okay? So you can rotate and reflect it, okay? So these are the 7 possible totally symmetric self-complementary box plane partitions, okay? So you can take this configuration, you can rotate it in any way that you want or reflect it, and you'll still get the same picture. Okay? So these were computed, as I mentioned, by Andrews in the 90s. Okay? So he gave the formula for them. Now, because of this reflection and rotation about these TSS CPPs, you actually only need to consider 1/12 of the box plane partition. So you don't need the whole thing. So you can just consider this configuration down here, and then it will repeat itself around the hexagon. So you just need this configuration here. And it turns out that these ones here are always frozen. So this one along this like diagonal are always frozen, and these ones here are always frozen. So you can actually reduce it to a smaller region. And then what you also notice is that if you go back here, so these are like lozenge tilings where you're just gluing together triangles. And if you glue together triangles, the dual grid of that is the honeycomb lattice. So you could just look at the dual graph, okay? And then you notice that you'll have like 1 hexagon on this left row, then 3 hexagons on this row, column, then 5 hexagons, and then it's going to be 7 hexagons, 9 hexagons, etc. And then this right boundary here is free. Okay, so you can have any configuration that you want here. Okay, so these just stick out. So these might be like matched or might not be matched, depending. Okay, so if we just take that graph and pull it out, we get this dimer graph. So this is the one where you've got 3 columns, sorry, 3 rows. This is the one where it's got 4 rows. And when it's even, you have to actually add an extra vertex because you need to have an even number of vertices, okay, because it's dimers. Okay, so each TSS-CPP configuration is then equivalent to a lozenge tiling on this subregion. Okay, so connection of triangles, which is then equivalent, if you look at the dual graph, to a dimer covering on these graphs. So a dimer is just an edge, and a dimer covering is a subset of edges so that each vertex is incident to exactly 1 vertex. Okay, so for example, here is a dimer covering of size 3. So you can see that every vertex here is covered exactly once by one of these red edges or blue edges. Okay. So if you don't like dimers, I won't take that personally. You can just think of paths. So you can think of like a path starting from each of these hexagons on the right-hand side. And this path just basically follows these dimers. So it starts here, goes left, then goes right, and then goes left. And we ignore what happens on this triangular part. This path here goes right, then goes right, then goes right. This path here goes right and then right. By the way, I should have mentioned that because of this free boundary, the standard way to get a free boundary in dimers is just to introduce triangles. So it's a trick from dimer theory. So this is why the triangles are there. Okay. Right, so next step is to translate what Zeilberger did into our language. So I told you that Zeilberger showed that the number of TSS-CPPs is equal to the number of ASMs. And actually, he proved a little bit more. He showed that some triangles in bijection, some triangles called GOGs, which correspond to ASMs, is equal to the number of triangles in TSS-CPPs called MAGOGs. And in particular, if you freeze off particular triangular regions and just look at trapezoid regions of these things, they also are equal. Okay? So what does that mean in our language? Okay? So in our language, his result means that if I freeze off this top face to have height n in the ASM, this corresponds to freezing off this vertex here, sorry, this edge here in my TSS CPP. Okay? And if I freeze off this triangle here to all have height n, this corresponds to freezing off this triangular region in my TSS CPP. And if I freeze off this triangle of size 3, then this corresponds to freezing off this triangle of size 3 in the TSS CPP. Okay. Now, you'll notice that actually I don't need this triangles on the. I just need the dimers on the bottom row, because if I freeze off these dimers here, then this edge is forced to be matched. Okay, because each edge must be incident to exactly. Each vertex needs to be exactly incident to exactly one edge. Okay, so freezing. I just need to freeze off the bottom row. So what that means is that freezing off this triangle here just means to freezing off these vertical edges on the bottom row. So in particular, if we look at the maximum of where this top path goes, this just corresponds to looking at the first time where we don't have a vertical dimer covering this vertex. Okay, so we can relate the maximum of the top path to the leftmost vertical edge not covered by a dimer. So these two things have the same statistics. Right. And because they have the same statistics, when you divide by the partition function, they have the same probability. So they're equal in probability. Okay. So what this means is that we've reduced this complicated object in ASMs, like the maximum of the top path, to an object on TSS CPPs, which is much easier to analyze, and they're equivalent in distribution. So if we want to know what the probability of the if we want to know the probability of the maximum of ASM's top path is k, then this just corresponds to the probability of that the number of TSS CPPs has k dimers vertical and then not 1. Okay. Right. So we then proceed in analyzing this event using dimer theory. Where we had formulas for K inverse. Okay, so I'm going to tell you a little bit about how we did that. Okay, so like for those that know that, like, you know, in lozenge tilings, this is or non-intersecting paths, this is like the leftmost point. You're looking at the fluctuations of the leftmost point in a free boundary. So as we mentioned, this is what you get is a GOE distribution. So this is, you know, why you see the GOE distribution. Okay. Right. So let me mention a few things about how we got this formula. Okay. So so for the TSS CPP graph, it looks like this, right? Okay. So this is one of size 2. Okay, so this is my TSS-CP graph. And I'm going to introduce a matrix called K. So this is the Castellane matrix. Okay. So K is just indexed by the vertices in my graph. Okay. And this is 0 if x, y is not an edge. Okay. And it's plus or minus 1 if x and y is an edge. Okay. Plus or minus 1, okay? So how do we get this sign? So this sign is something called the Castellane orientation. And it's an orientation where you, for each face of the graph, you need the number of counterclockwise edges, or anti-clockwise edges to be odd. Okay, so on each face, as I go around, I need the number of counterclockwise, anti-clockwise edges to be odd. So I've got 3 counterclockwise, so now I need 3 going clockwise, okay? So that would be a valid Castellane orientation. So this is the Castellane orientation. Okay. And so if my x is here and my y is there, then this is going to be a -1. But if my x is here and my y is there, then it's going to be a +1. Okay, so these signs give me this sign here. Okay. Right, so Castellane's theorem showed that in the 60s, showed that if you compute the Pfaffian of K and take the absolute value, this is the number of dimer configurations. So Pfaffian of K, in this case, is number of TSS CPPs. Okay. Okay. Yep. Every hexagon. Oh, triangles, you also need counterclockwise one. Odd. So let me just do it. So you'd have this and that, right? So I need counterclockwise, number of counterclockwise edges, odd. So I've got 2, which is an even number. And so I need another one so that it goes that way. Right, so Castane's theorem says that if you compute the Pfaffian of K, this is equal to the number of TSS CPPs. But another theorem, or an analog of Kenyon's theorem in 1997, is that if you look at entries of the inverse Castellane matrix, this gives you local statistics. Okay, so if you can find the inverse of the Castellane matrix, then you can find all the statistical information that you want. So essentially, we boiled our problem down to find K inverse. Okay, so find K inverse. Okay, so there's a few steps on how you do that for this model. So I'll just outline the steps. So I'm going to let these points here, these ones here, be the top boundary, and all the other ones to be, all vertices to be V. So V equals set of all vertices, okay? Right, so the first thing that we did was that if we look at K inverse of the top boundary, and this special vertex B, so this is just the last one, okay, so we could actually guess this formula. Okay, it's just when we looked at it, well, when we looked at entries, it just looked like entries that we knew already, so we just guessed it. Okay, so we guessed. Okay, so we guessed some entries. Okay, then what we did was, so this is for X in this top boundary. The next thing is that if you look at the matrix K times K inverse, and you look at this entry rise, this gives a recurrence relation. And what we did, what we can use this is that if we use this on this thing here, we can move all our vertices, or the ones that we don't know, into the interior. So we can use this recurrence to get K inverse XB for now X and V. So use this relation, use K times K inverse is XB is equal to the identity, or identity when X is equal to B, to find K inverse XB for X in V, okay? And this is only using part of this formula, okay, of this recurrence. And we can use the rest of this to actually verify that this relation, K inverse XB, is actually right, okay? So the second step is again, use K times K inverse XB is equal to the identity X is equal to B to verify K inverse XB. Okay. So what you can think of this is there's two steps. I've moved my X using this recurrence relation from these points here down to all points, to all vertices in the graph. And then I've used the equation again, because I haven't used everything, to actually verify like that this formula K inverse XB is actually correct, because I've got a linear system of like n equations, or number of vertices equations with number of vertices variables. Okay. Right. So this gives us K inverse XB when B is this bottom boundary. So how do we get K inverse XY where Y is another point in the interior, so where Y is not B? And the way that we do that is we use this thing. So we use Dodgson condensation. So to get K inverse XY, so for XY in the top boundary, use Dodgson condensation. Okay. Okay. So this means we've got K inverse XY, where XY are both on the top boundary. And now we just use K times K inverse just to move these formulas down, because this just defines a recurrence. Okay, so we can now move the Y coordinate and the X coordinate down, and that just gives us K inverse. Okay, so and that's how Arvind and I found formulas for the inverse Cassidy matrix. So, okay, right. So let me just summarize and conclude. So what we did was for this six-vertex model with delta is equal to 1/2, or ASMs, we first introduced a set of well-defined lattice paths. Okay. Yeah. Oh, okay. I didn't write this full step. So move X and Y into V by using K times K inverse, because you're assuming that K is the inverse, right? Or you know that K inverse is the point. Yeah, it's an unknown, so you just use this entry-wise. Okay. K inverse K is the identity. Okay. So this one moves the left coordinate, and this one moves the right coordinates when you hit it from the right-hand side. Okay. So to summarize. So we introduce these well-defined set of lattice paths. Then the limit-shaped curve of this ASM is just given by the boundary of this top path. And then we showed that the fluctuations of this maximum of the top path is given by the Tracy-Widom GOE distribution by comparing to the TSSCPP model. And we also gave a conjecture about what we would like to prove, which is fluctuations of this top path. Okay, so thanks for your attention.
Are there any questions?
So you mentioned on the first part of the program is to guess the K inverse XB. How did you guess it?
Oh, we just looked at it entry-wise, and there was like a formula that we knew from other things. So we just used that, and then it was just very like it just satisfied this nice pattern. So it was just like, oh, it's this, and then we moved it, and then used this recurrence thing, and then it was like, okay, it's correct. So we got it for like n is equal to 10 or something, and then we were like, okay, this must be true.
Okay.
Yeah. But for other models, you can't do that. Like sometimes you actually have to, you can actually you don't need to do this guess. So this is maybe a drawback in this, that you actually need to guess one entry.
Thanks. So there's one sort of global question that I don't understand. So counting dimers is what in the physics language we call a free fermion problem. It's a
Right.
Grassmann, Pfaffian is the Grassmann interval of something. And, but counting alternating sign matrices is, as far as I know, not a free fermion problem. Certainly if you look at the six-vertex model at that value of delta, that's not free fermionic. So how do so you told me, very possibly I don't understand this correspondence you talked about at the beginning between counting alternating sign matrices and the TSS-CPP problem versus the Cooper-Berg method, the six-vertex model method.
So I guess the way that Zeilberger did it, and how people like Fisher have been looking at it, I think I don't think they can reconcile the fact that one is delta is equal to 0 and one is delta is equal to half. Right. What they do is that they have these constant term formulas that looks very similar to what Colomo and Filippo and Franco did, and they have one constant term formula for ASMs and one constant term formula for TSS-CPPs, and they just show that they're equal. So there's nothing constructive to go between one to the other.
So that's why this map isn't.
Yeah.
But that says there's something free fermion hidden inside, or doesn't it say there's something free fermion hidden inside the delta equals
many things count the same thing, right? So I think it might just be a flip. Maybe Paul's got better suggestions.
We showed that there was some refining, what we proved to be refining correlation conjectures. But the point is that these are always boundary correlation functions. It's all, you never find bulk quantities which agree in both models. They're always just boundary effects, which is a bit different, which is the same type of thing that you've been using. I think this is really, these boundary effects are they're not telling you anything about the model of models.
The bulk is on the boundary, they are predetermined.
So saying, is that you agree with? But it's actually said
just physical picture for predetermined, for interacting fermions on a boundary when density is small. The interaction doesn't matter, so the predetermined on the boundary.
Yeah. Okay, that makes sense.
I think I actually asked you this before, but maybe I'll try again. So in these free boundary problems, the ones that I know at the very least, there's a way of putting in a parameter naturally in, for example, representation theory. And that parameter gets you from GOE to GSC to even Gaussian if you want. Is there somehow, I don't know, you count the number of points that have odd height or something? Can you think of anything natural?
Probably you can do Q to the volume, or something as you say where you.
Oh no, just something for the boundary, not for the whole thing.
I guess you could put in an extra parameter, but I don't know how to invert the matrix then.
I see.
Because this was just like, let's play with some numbers, and then we spotted some pattern, right? But
right.
It's a good question. I don't know how to do it.
So just you explained us how to compute k minus 1, but you never showed us an expression for it. So is it too horrible for our eyes? Or?
Well, okay. The expression that me and Arvin got was another one of these long expressions, but it's got like nice structure. So this is what we found, what Kurt found. Like there's a nice structure inside of it, but the expression that we got was just like basically we just dumped the expression that we basically got, and we didn't try to simplify it. So once you simplify it, there are some nice things. So there's like there's Catalan numbers in there, for example. So
it is in your paper with of last year.
Sorry?
It is in your paper from these expressions are in your paper from last year.
Yeah, it's in both, like the one with Kurt and also the one with Arvind, yeah.
Okay.
Well, if there are no more questions, let's thank the speaker again. And we start back in 15 minutes.